follow the sound, and it'll record what's on the screen.
Okay. Did you take a video for what we have done so far?
No, I have the hard copy, but I didn't do the video yet. I just remembered as we were doing this. Sorry.
No, it's okay. But we still have the copy, so I will rewrite it and then start it.
Okay. So this is a really important theorem, and so here's something we have to look at a little bit. Okay, we need to look at what a least upper bound is. So a lot of times you want to prove that something's a least upper bound. Okay. So we know what it is now, right? We know that
Yeah.
given a a subset of the reals that's not empty and that's bounded above,
okay, then it has least upper bound.
Right. We're going to say that gamma is, and we do it like this. We say least upper bound of A.
Okay.
Or sometimes your book uses a different way of saying this. It uses this, the infimum of A. This is pronounced infimum.
Okay.
And infimum is Latin. It means smallest.
Okay.
Okay. So this is the least upper bound of A if and only if, first of all, it's an upper bound, right? And if beta is any other upper bound of A,
okay,
then gamma has to be less than or equal to beta, right? Because this is the smallest upper bound, right? So you give me any other upper bound, it has to be more than this or equal to, right?
Yeah, so for our example is like 1 and 2. 1 is 2 is beta.
Yep.
1 is gamma.
Exactly. So if you have any other upper bound, I know that it can't be less than this. This has to be the smallest one, right?
Okay.
Yeah. Now there is a really important corollary in your book, and I'm going to show you where it is because you want to really understand this well. It's right. Hold on. Here it is. Yeah. Right. So here we say, it's at least upper bound if it's an upper bound, and if you have any other upper bound, it has to be greater than or equal to. Okay. So these are important. So let me just, if you don't mind, let me just put these definitions in here because these are really important definitions.
Okay.
So we'll put these in this right here. So this is an important definition. I guess this is it. So that's bounded above and bounded below, and
that's what we have. Yeah, we did bounded above.
Yeah, we actually didn't do bounded below, but the same thing is true. You can do the same sort of thing. If you have a non-empty subset that's bounded below, it has a greatest lower bound.
Could we do it?
Yeah, sure. So there's another version to this also. So this deals with something called the greatest lower bound. And let me just draw a picture, okay?
Okay.
So let's just suppose A is like here. This is A. Okay?
Okay.
And we'll call this small a. We'll call this small b, okay?
Okay.
And we'll call this capital A, this set. Okay.
Okay.
So we know that A has a least upper bound, right?
Yes, we have done that.
So what is the least upper bound here in this situation?
It's B.
That's right. B is equal to the book likes to use this. I like least upper bound. He doesn't care what you do, okay? Either one's okay. Okay. But notice that there's also a thing called the greatest lower bound. Notice that all of these numbers here are lower bounds.
Okay.
So what does that mean? Well, to be a lower bound, we're going to say alpha is a lower bound of A.
Okay.
How should I make this definition? What should alpha have to satisfy?
Yeah, alpha should be greater or equal or smaller than or equal A.
That's right. Smaller than or less than x for all x in A, right?
Yes.
Good. Okay. Now notice the same thing applies. There is a greatest lower bound. These are all the lower bounds. There is a greatest lower bound, right?
Which is A.
That's right. So in our case, A is the greatest lower bound of A. Okay. So that's what we're doing here. So this actually is a consequence of the completeness axiom. Okay.
Mm-hmm.
And that's okay. I won't go into the proof, but you can prove that if the completeness axiom is true, then a greatest lower bound has to exist for every non-empty subset of the reals bounded below. Okay?
Okay.
Okay. Now,
do we have example for the upper and lower bounded?
Sure.
Yeah, so example we can pick from the book and solve.
Yep. So the one last thing I want to go through before we do that is there's one last important fact, and that is
okay.
Nope. Hold on. It's a lemma in your book. Where is it? Here it is, right here. This is an extremely important fact.
Okay.
Here we go. So what this says is if you have some subset of the reals, and you have an upper bound for it, okay?
Mm-hmm.
Then this upper bound is, and I take that back. This isn't infimum. It's called the supremum. I meant to write supremum because supreme means greater. Okay.
Okay.
Yeah, this should be supremum, not infimum. Let me erase that. This is the supremum of A.
Okay.
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 Okay. So this is the supremum of A if and only if for every epsilon there is some element of A that is within epsilon of S.
Actually, I didn't understand this lemma.
That's okay. This takes a little while to understand. So here's what it's saying. So here's S, okay?
Mm-hmm.
And I'm going to claim, and it's an upper bound for A, but I'm claiming it's the least upper bound. Okay?
Okay.
And what this means is, in order for this to be true, if you give me any epsilon, okay?
Mm-hmm.
Any epsilon neighborhood,
mm-hmm.
I have to be able to find some element of capital A in that epsilon neighborhood. Okay. So notice that A has to be greater than S minus epsilon. This is the point S minus epsilon, right?
Okay.
So there has to be some value of A greater than S minus epsilon.
Which one is the point is S minus epsilon? That point, that dash?
Here, let me put everything in the same color. So this guy here is S minus epsilon right here.
Uh-huh.
Okay. And what the theorem is saying is that for every epsilon, I have to be able to find some value of A
Okay.
That's between S minus epsilon and S.
Okay. Okay.
Now, when you think about it, that has to be true. Because suppose it wasn't. Suppose you said, no, that's not true. Suppose you could come up with some little epsilon so that everyone was below S minus epsilon, right? Well, notice this would be the new least upper bound.
Yes.
Okay, you would have an upper bound less than the least upper bound, and that can't happen, right?
Yeah.
Okay, so that's what we're saying. We're saying that when there's a least upper bound, there's always someone as close as we want to S.
Okay.
Okay, good. Okay, so you had some homework problems from here, if I remember correctly.
Yes.
They were good problems too. They were hard problems. Do you want to take a look at those?
Yes, please.
Okay. So let's see.
Are we in chapter 2 or 1?
This is chapter 1, actually.
Okay.
Yeah.
So is this the things we have to understand from chapter 1 to move to chapter 2?
Yeah, the completeness axiom is a really important axiom. If we want to, we can skip these homework problems and go into the sequences. But
I mean, let's do some of them.
Okay. So let's see. Okay, 1.3 is pretty good.
Okay.
Okay.
I need first to understand the question. So
right. Okay, so let's look at this. Okay, so we have A and B are non-empty.
Okay, bounded above. And satisfy B included in A. Show sub B less than or equal sub A. So it's non-empty and bounded. That's the theorem we have looked at. And so it should have least power bound, right?
That's right. So we know that A has the least upper bound, right?
Yes.
So A is non-empty subset of the reals, bounded above, blah, blah, blah. So there exists an alpha in the reals such that alpha is the least upper bound of A. And the same is true for B, right?
Yes.
Least upper bound of B. And now we want to show that beta has to be less than alpha.
Beta, sub beta have to be less than sub A.
Right. And this is the same as sup. This is the least upper bound. This is the same as sup A. It means the same thing.
Okay.
Sup B. Okay?
Okay, so instead of this question, you want to show that beta less than alpha. Okay.
How do we do that?
So could we draw a line? I don't know.
Sure. Let's get an idea of what's going on. Sure. Okay. So A is a subset of B. So let's just draw something that's a subset. So we could let this be B, right?
Okay.
And it could lie, it's going to lie inside of A, right?
Okay.
So maybe this is A.
Okay.
So this supremum would be here, right?
Yes.
So it makes sense. Okay, but we have to prove it now.
So let's say B minus alpha over 2, that's the center, right?
Let me see. So what was this again now? Say that again.
So beta minus alpha over 2.
Okay. So that's
right, less than epsilon.
So beta. Okay, beta minus alpha over 2. Okay, we could let that be epsilon. Okay.
Okay, so we want to show beta less than.
But hold on for a second. Something could go wrong with that. What if capital A was equal to capital B? Right? So we could have a situation like this. They could be the same set, right?
Mm-hmm.
So there, that would be equal to 0, and epsilon can never be 0 in our proofs, right?
Yes.
All right. So we have to be careful.
Yes.
Okay. Or even if that didn't happen, you could have something like this. You could have a situation where the upper bounds were the same, right? But maybe A was longer. Okay?
Yes. Yeah.
A lot of different things can happen here. So we have to be careful when we draw diagrams.
Okay, so I would like to suppose there is an element greater than beta and smaller than alpha.
Yeah, but what if what if the endpoints are the same? What if alpha is equal to beta?
That's a problem.
Yeah. See, then we run into difficulties. They could be the same, and these sets could still be subsets of each other, right?
Yes.
So can I give you a hint?
Yeah, please.
Let's try proof by contradiction.
Oh, what's that contradiction? What we have done up?
So here's what we're trying to prove, right?
Okay.
So proof by contradiction assumes the opposite is true.
Oh, yeah, I get it. Okay. Go ahead.
So what are we going to assume? We're going to assume that beta
bigger than alpha.
That's right. Beta is greater than alpha. Good. Okay. Now we can draw a picture. If this was true, we can actually draw a picture, right?
Okay.
So now we're saying that they look like this. That beta is like this. That alpha is like this. And we have to be a little careful. The sets can be kind of weird looking. So you could have something like this, right?
Mm-hmm.
Okay.
Okay.
Now I'm going to use that lemma. I'm going to use that lemma to prove that this can't happen.
Okay, how?
Because now we can do what you just wanted to do a second ago. Notice you had this beta minus alpha. Now this makes sense, right? Because I'm assuming beta is greater than alpha, right?
Okay.
So I'm going to let epsilon be equal to beta minus alpha. And this is positive now, right?
Yeah.
Because I made this assumption. I said this had to be true, right?
Yes.
Now, what does it mean for beta to be an upper bound of B? Let's think about this. This is beta minus epsilon, right?
Yes.
Okay. What did the lemma tell us? It says for every epsilon between beta minus epsilon and beta, what has to be true? Whoops.
Where's the lemma? So
here's my beta. Here's my beta minus epsilon.
So there's so beta minus epsilon should be less than a point between beta and beta minus epsilon.
Right.
Or beta, yeah.
Right. It says that there's somebody in capital B. We'll call it small b, okay?
Mm-hmm.
That has to lie in here, right?
Yeah.
Okay. Now we're getting somewhere. Because this is going to lead us to something that doesn't make any sense now.
Okay.
So now we know that there exists a B in capital B such that beta minus epsilon, which is equal to alpha, is less than B is less than beta. Okay?
So B minus epsilon equal to alpha less than B less than Beta, yeah, but beta is subspace of but sub B is subspace of A, so
right, and that's the problem, right?
Yeah.
Because now this is an upper bound. This is the least upper bound of A, right?
Yes.
This is an upper bound of A, right?
Yes.
But that can't happen. Because now what we're saying is that B is greater than every element in A. But this this contradicts the fact that B is a subset of A. That can't happen, right?
Yes.
And so this can't happen. Okay?
Yes.
Therefore, that has to be true.
Yes.
Excellent.
Easy. Yeah, easy.
Yeah. So, but do you see how powerful that lemma is? It's a really powerful lemma. You'd have a really hard time doing this proof if you didn't use that lemma.
Yes, it is.
Very, very good lemma. Okay.
Mm-hmm.
So here's what's important. Okay. So let's go back to sequences for a second. Okay. So with sequences, we have the definition of what it means to converge. Okay. But
that's what we have done up.
Yeah, but now here's the problem. Here's the real problem. Given a sequence, we want to know, does it converge?
Or not?
That's right. Does it converge, first of all? We'll call this x sub n. So does x sub n converge? And then the second question is, well, if it does converge, what does it converge to?
I cannot read. Given a sequence xn, what's the...
Yeah, does x sub n converge? Here, hold on.
The things before... Yeah, it's number 1, 2.
Question 1,
Okay.
So does x sub n converge?
So when the question gives me a sequence, I should ask myself, does this converge or not?
Absolutely, yes.
Okay.
And then the second question is, if it converges, what does it converge to? Okay.
Okay.
What does it converge to?
Okay.
So there's a very important theorem. It's called the Monotone Convergence theorem. So if you go back to chapter 2, hold on.
2 or 1?
Chapter 2 now.
Okay.
So if you go back to chapter 2, there's this thing called the Monotone Convergence theorem.
Okay.
And so here's what the Monotone Convergence theorem says. It says, if you have a sequence that is monotone, so we have to define what monotone means, right?
Yes.
So let's find this part here. Still gotta go. So we know what a limit is. We know what it means to converge. This is pretty straightforward. I don't think this section is. It's just basically saying. I'm going to go through it real quickly, but we won't spend a lot of time on it. Basically, it says. Well, this I take that back. This is actually important. There is one theorem that's important here. A sequence has to be. A sequence has to be bounded if it converges. This is an important theorem.
Okay.
Because this answers the first question. Okay.
Every sequence is bounded.
Every convergent sequence is bounded, right?
Convergence, yeah, okay.
So this is the following.
So I should show it's converged, so it's bounded.
And here's how we use this theorem. And here's why it's important. So this theorem says that if xn converges, then xn is bounded, right? Okay.
Yeah.
Now, when we do math, this, if I want to write this in mathematics, we write this. This is the statement P, and this is the statement Q, right?
Okay.
And we write this as P implies Q, right?
Okay.
So a sequence is convergent implies the sequence is bounded, right?
Okay.
And so what I'm going to do is I'm going to write this in a different form. This is actually the same as this. This means not. This little thing here means not.
Yeah.
So this says that if a sequence is not bounded, this implies it does not converge.
Okay.
So, and here's why this is true. I want to show you real quick because this is actually important. So, P implies Q means that P sits inside of Q. Okay. So this
P sits inside Q.
Right. So this says the set of all convergent sequences lies inside the set of all bounded sequences, right? Okay. Because if you're in here, you're in here. Okay. So everything outside of here is not Q. These are all the guys that are outside of Q here, right?
Okay.
So notice that if you're outside of Q, you're outside of P also, right?
Yes.
Okay. Here's how we use this. So the way we use this is we use this as the following. If xn is not bounded, then what can we say?
Q is not xn is not sequence. Converge sequence.
It doesn't converge. That's right. Does not converge. Why is this so important? Well, because notice the first question I asked was, does it converge? Okay? So if you know that the sequence is not bounded, you automatically know the answer to this question. It's no, right?
Yes.
Okay, so good. So that's an important theorem.
So do we have a question that asks us those two? Do we have exercise that asks to show those two?
Sure. Let me go ahead and look. Let me go look. This is another theorem, and I won't go through it. This is a pretty simple theorem. It just says that if you have two sequences that converge, then the limits of these sequences behave like you would expect them to. I'm just going to put this in here, but I won't prove it. This is pretty easy. It's important, but I don't think we have to go through this, okay?
Yeah. What it says?
So okay, so the first one says that if you have some limit an that converges to a, and now I make a new sequence, which is c times an. I multiply every element in the sequence by c.
Okay.
That converges to c times a.
Okay.
So notice what this is saying. This is saying that the limit kind of like distributes, right? This says that the limit of c times an, as n goes to infinity, the c factors out actually.
Yeah.
Okay. And this is c times a. Notice that limits also distribute over sums of sequences, right? They also distribute across products. This is not so obvious, maybe. This one may not be obvious, but it's true. And they also distribute across quotients, as long as the limit of bn is not 0. Okay?
Yeah.
Okay, so that's not so bad. Okay, so let's look at some problems here. Let's see.
Yes, please.
Okay, so there's none here. That's okay. this is an important theorem too, because this is going to give us the squeeze theorem. This is an important theorem because there are three theorems that are important. Let me just show you real quick. This is the first theorem that's important. Okay. This theorem that I'm going to show you, it is kind of like a lemma to the squeeze theorem. It says that if you have two sequences that both converge, okay, and an is always less than or equal to bn, okay, then the limit of an is less than the limit of bn.
Okay.
Okay. And we're going to need this for the squeeze theorem. Okay. So this goes with the squeeze theorem. You know what the squeeze theorem is, or the sandwich theorem, people call it. You've heard of that, right?
Actually, no.
Okay, that's all right. That's all right. So theorem 2 actually consists of two theorems. This is the first theorem. Here we go. And we need this to prove the squeeze theorem. Here's what the squeeze theorem says. Because notice now we want to answer the question, what if the sequence converges, okay? What does it converge to?
Yes.
So the squeeze theorem is going to answer that. Where's the squeeze theorem? Oh, come on.
People call it sandwich theorem?
Some people call it the sandwich theorem, yeah. It should be... Hold on a second. Let me... where is it? I do want to find it for you because it's an important theorem. Let me look in the book real quick at the very end. For some reason, it's not. It's in here, but I'm not finding it. Let's see. Here we go. Squeeze theorem 49. Okay. Go back to 49. Okay. Okay, here we go. So where did I, hold on. Oh yeah, 49. Oh, here we go. Okay. Yeah. Here it is. Oh, they put it as an exercise. Interesting. Wow. Oh, okay. This is the main theorem that we want.
Okay.
And since it's an exercise, we could actually prove it if you want. I mean, it's a
please.
Very good
I would
exercise.
like to know that's it.
Yeah, this is an important theorem. So let's go ahead and prove this. So first of all, I don't know if we want to prove these or not. Let's assume these are true. Okay, let's go ahead and assume this is true. And so we're gonna look at the squeeze theorem. So the squeeze theorem says two things. It says that we have three sequences, right? Okay.
So there's this three sequences.
Mm-hmm. So the first thing I know.
So okay.
So I know this is true, right? For all n.
Mm-hmm.
But I know something else. I know that these sequences at the end converge. Okay. So I know that.
How do you know that?
That guy right there.
Okay.
Okay, now we're ready. Whoops, Zn. There we go. And so notice what's happening. Here's what's happening. Let's just draw a picture of what's happening here. Okay. So what's happening is like maybe x1 is here, z1 is here, right? And maybe y1
Could you go up the page?
Oh, yeah, sure, no problem.
So,
okay. So maybe like x1 is here, z1 is here, and y1 is here, right?
yes.
This is going to be L. Now notice that xn is converging to L, right? So maybe x.
Yes, that limit goes to L.
And notice that y2 always has to be between them, right?
Yeah.
So you see what's happening is x is coming from this direction, z is coming from this direction, and it's squeezing yn. Yn has to converge to L also, right?
Yes.
Okay. So we have to prove this.
So the limit of x1 goes to L.
Yep.
That's what about x2 and y2, c2?
Well, these are just elements in the sequence, right? So we know that z is converging to L. So z1 may be here, z2 may be here, z3 is getting closer to L, right?
Okay.
So we can see what's happening is these guys are squeezing y. They're forcing yn to go to L. So now we have to prove this. Okay, so let's see. So let's see. How do we want to prove this? So we want to prove that the limit of n goes to infinity of yn is equal to L. Okay. So so let's see. So first, let's see how we're going to do this. Okay, so let's go ahead and use the limit definition. Okay?
Okay.
Okay, so let's use the limit definition. So let's let epsilon be greater than 0.
Mm-hmm.
Okay. And let's see. I know that there exists in nx in the natural numbers. So for all n greater than or equal to nx, xn minus L has to be less than epsilon.
Yes.
And I also know that there is some nz because...
So this is a definition of the converge.
Right. And this is true because I'm given that xn converges to L, right?
Yes.
Now zn converges to L also. So there's also some natural number nz.
Mm-hmm.
So for all n greater than or equal to nz, I know that zn minus L is less than epsilon. Okay?
Yes.
Okay. So what I'm going to do is I'm going to choose the larger of these two. Okay, I'm going to let capital N be equal to the maximum of these two.
Okay.
Okay.
Mm-hmm.
So let's see what happens. So for all n greater than or equal to capital N, let's look at yn minus L. Okay?
Okay.
Okay. So let's see. See how it's going to work. Actually, let me do this. Let me try this. Okay, yn minus L. Okay. Okay, I can write it like this.
Yn minus xn plus xn
minus
L.
Okay, and I can also write it like this. So this is a little tricky. I can also write this as yn minus, and this is actually less than or equal to. This is the triangle inequality I'm using, right?
Yes.
Okay.
Yes.
Okay. Plus zn minus L. Okay.
Mm-hmm.
And now I can use the fact that these guys are less than epsilon. Okay. I'm going to use the fact that these guys are each less than epsilon. So here's what I know. I know that xn minus L is less than epsilon, and zn minus L is less than epsilon because I chose the larger of these two n's, and so that if n is greater than this, n is going to be greater than x sub n, so this will be less than epsilon, right?
Can you go out by the bridge?
Sure. Okay. So I chose this guy so that when everyone's greater than him, this is less than epsilon, right?
Mm-hmm.
And I chose this guy so that when everyone's greater than him, he's less than epsilon, right?
Yeah.
And I chose this one so he's bigger than both of these, or he's at least as large as both of these, right?
Okay.
So when small n is greater than or equal to capital N, both of these will be true, right?
Mm-hmm.
Okay. So now I'm going to rewrite these. So now I'm going to say yn minus L is less than or equal to, and I'm going to take off the inequalities because I know that xn minus I know that yn minus xn is going to be greater than 0. Okay. This actually becomes
because it's plus epsilon.
Yep. And so I know that yn minus L here is going to be less than zn minus yn plus epsilon. Okay. And so when I add these,
you did switch the zn and yn, no problem.
Right, because I know that this is positive, and I know that this is positive here.
Okay.
Okay, let me see real quick. Is this how I want to do this? So when I add these, I'm going to get yn minus L is less than zn minus xn over 2 plus epsilon. I'm going to add these and divide by 2.
Okay.
Okay, and this is true for all n greater than or equal to n. Okay.
Okay.
So let me see if I did this. This doesn't look. I don't think this is what I wanted to do. It's not giving me what I want. Let me think for a second. I know of one way to do it. It's a little bit long. This isn't quite giving me what I want. So let me just think for a second. Let me try to use these up here.
Mm-hmm.
Let me think. There exists a C such that let me think. Oh, shit, it's so easy. Okay. It's very, very easy. Okay, hold on.
Mm-hmm.
So here's what I know.
So what we have done so far, was it helpful?
We don't need to do that, okay? So here's what we know. This is a really easy way of doing this. We know that xn converges to L. We know zn converges to L. So here's what we're going to do. I'm going to subtract xn from here. I'm going to do this. I'm going to say 0 is less than or equal to yn minus xn, okay, which is less than or equal to zn minus xn.
Okay.
Okay? So here's what I know. I know that the limit of xn goes to L, the limit of zn goes to L. So I have a theorem that tells me that the limit of zn minus the limit of xn goes to 0.
Okay, so the limit of zn goes to L, and the limit of xn goes to L.
Right.
So when, it's equal to 0. Yeah, it should be.
Right. So this sequence converges to 0. This is greater than or equal to 0. So now we want to show that this sequence also has to go to 0, okay?
Okay.
But this is easy to show. This is very easy to show. So this is some new sequence Wn. I'm going to call this Wn, right?
Okay.
So now I have to show that Wn goes to 0, right?
Okay.
But that's easy because since this goes to 0, this is easy. Since Zn minus xn converges to 0,
okay,
for every epsilon greater than 0, there exists some capital N such that for all small n greater than or equal to capital N, Zn minus xn is less than epsilon, right?
Okay.
But notice this guy is less than it. He's positive, and he's less than this.
Okay.
So since 0 is less than yn minus xn is less than or equal to Zn minus xn, it follows that this also has to be less than epsilon for all n greater than or equal to capital N.
Okay.
Therefore, we know that yn minus xn converges to 0, right?
And the limit
xn converges to L. So when I take their sum, the limit of yn minus xn plus xn, this converges to L, and that's the limit of yn.
You add xn.
Right, because remember that theorem that says that if an converges to A and bn converges to B, when you add them, it converges to A plus B, right?
Yes.
So this is the sequence. This sequence is like my ANs, this is like my BNs. When I add them, these cancel.
Yeah.
And I get limit of yn goes to L.
Okay.
Okay.
Okay, cool.
So the reason why it works is because this goes to 0, and this forces this to go to 0, right?
Yes.
And that's how the squeeze theorem works. It squeezes this limit and makes it go to 0 also. Notice something that's very important is that this also uses this theorem uses these theorems right here also, right?
Yes.
So I'm using that theorem there also. Okay. Very good theorem. Okay, one last theorem. I said there were 3 theorems. There's one last theorem we need to know. This is called the monotone convergence theorem. It's very important.
We need to know for all chapter 2 those theorems, or you mean for sequence?
If you know these 3 sequences for chapter 2, you pretty much can do everything.
Cool.
These are the 3 main sequences.
Okay.
So this is sometimes called the Bolzano-Weierstrass theorem. People call it different things. You know, somebody invents it and they want to call it after it, you know. Okay. But this is what it's based on. So just like the last theorem had 2 theorems, this has 2 theorems also. This is like the pre-theorem. Okay. So this is the first part of the theorem. So this is a really important theorem. We should stop and just think about this for a second. Woo! What happened there? Heck. Oh, come on. There we go. So it says if you have a sequence that's monotonic, okay, so we have to know what monotonic means, okay?
Yes.
Here we go.
This monotonic.
And what monotonic means is that a monotonic sequence is a sequence that never decreases or never increases. So let me move this down here.
So let's understand the monotonic.
Yep.
And decreasing and decreasing.
And it keeps wanting to get bigger. Right. So it means that the sequence is always. You have to be a little careful. It doesn't mean that it's always going up. It can be equal to its. It can stay the same at certain points. Okay. Oh, come on, pain.
Could you explain it more?
Yep. So here's an example. Let me give you an example of a monotonic sequence. Okay.
Okay.
So here's a monotonic sequence. This is monotonic decreasing because x to the n is always greater than or equal to x to the n plus 1. Right? Because 1 over n is always greater than or equal to 1 over n plus 1 for this sequence,
yes.
right? Okay. So
yes.
So people write this like this. They say it's monotonic decreasing. And they use a little downward area. And what it means is these guys are getting smaller and smaller, right?
Yes.
Now you have to be careful. Monotonic decreasing does not mean that these guys have to be getting smaller. Here's another monotonic decreasing sequence. Minus n. Okay? So this is -1, this is x1, right?
Okay.
-2, okay? But notice this is diverging to negative infinity, right?
Yes.
But this is also monotonic decreasing.
How's that?
Because if I look at any element or any term in the sequence, the one after that is always less than or equal to, right?
The one after that is less than the original one.
Right, because it always lies to the left, right?
Mm-hmm.
These guys are going this way. Okay?
Okay.
So what it means is that if you look at any term in the sequence, all the rest of them have to lie to the left of that term.
Okay.
Okay. Now you can have monotonic increasing also. If I had x sub n is equal to positive n, that's monotonic increasing, right?
Let's see it.
Yeah. It's down. Okay. So if I write like x of n is equal to positive n, let's just take a look at where these guys are. Okay, so this is 1 is x sub 1, right? 2 is x sub 2, 3 is x sub 3. And so what this means is if you pick any guy in here, x sub n, right?
It would be greater than xn.
Right. And here's a very important idea with sequences. We talk about the tail of a sequence, okay?
Mm-hmm.
The tail of the sequence is all of the guys after a certain term, right?
Mm-hmm.
It's kind of like a tail of a dragon, right? It's like, it's everyone after this, okay?
Yes.
So this is the tail of the sequence after x sub n, okay?
Yeah.
They all lie here. They all lie to the right of x sub n, right?
Yes.
Okay, so this is an example of a monotonic increasing sequence.
Xn less than or equal xn plus 1.
Yes. So it says that if you pick any term in the sequence, all the rest of the elements in the tail of the sequence are going to lie to the right. Now you have to be careful. Some sequences are neither. For example, here's a very famous sequence. X sub n is equal to -1 to the nth. This sequence, x sub 1 is -1, right? X sub 2 is +1. X sub 3 is -1, X sub 4, X sub 5, X sub... So this is neither increasing or decreasing, right?
Okay, I see.
It's bouncing all around, okay?
Okay.
Okay, so what this theorem says, this theorem says that if you have a sequence that's monotonic and bounded, bounded is really important, then it converges.
Okay.
So let's take a look at what it's saying. Let's just suppose that if it's monotonic, it can be monotonic increasing or decreasing, okay?
Yes.
So let's just suppose it's monotonic increasing, okay?
Okay.
I know that it's bounded, so there's two numbers here that contain everyone, right?
Yes.
Okay. So x sub n is in here. X sub 1 is here, right?
Yes.
If it's monotonic increasing, where does x sub 2 have to be?
Sorry?
Okay, so if this sequence is monotonic increasing and x sub 1 is here, where does x sub 2 have to be? Can x sub 2 be here?
No, on the right side.
Exactly. Right, so these guys are getting larger and larger, right?
Yes.
So notice that we can prove, this is easy to prove, because notice that the set of all x sub n's, this is a subset of the real numbers, right?
Yes.
They're non-empty, right?
They are bounded.
And they're bounded above. So what do we know?
So it has the least bound.
Has the least upper bound. And that least upper bound is the limit. This is the least upper bound. And you can prove that this is the limit. And when you think about it, it makes perfect sense because, whoops, sorry, I don't know why I did that, least upper bound. Because what does it mean to be a least upper bound? It says that for every single epsilon, right, there has to be some guy in here, right? And notice, right, and notice that once this guy is in here, all the other guys have to lie above him, right?
Yes.
So now that's what it means to converge. It means that for every epsilon, there's some n such that everyone else after him has to be within epsilon of that number, right?
So what about the limits after alpha, between alpha and b?
Well, there isn't anything. There isn't anything because this is the least upper bound, right? So it's really important to realize that if you're a least upper bound of a set, you can't have any element of that set above you because now you're not a least upper bound.
Yeah, but I thought the least upper bound is b.
No. It's just an upper bound. Okay. And remember, the upper bound is not unique, right?
Yeah, but I don't know. I thought b is the least upper bound.
Well, okay, I just used the fact that it's monotone and bounded, so I just drew any upper bound. B here is just any upper bound. I know that one exists, right?
Yes.
Okay, so now my theorem says that if it's non-empty and bounded above, there's some upper bound, there's a least upper bound.
Okay.
So now I got my, and that's going to be the limit. It turns out that the limit of x sub n, as n goes to infinity, is actually equal to the least upper bound.
Okay, the limit of xn is okay.
Right.
Okay.
And you can prove that using that lemma, because first of all, we know the least upper bound exists, right? And for every epsilon, what it means to be a least upper bound is that for every epsilon, there has to be some guy between this within epsilon of alpha, right?
Yes.
And since this is increasing, if he's within epsilon of alpha, everyone else has to be even closer to alpha, right? And that's what it means to converge.
Yeah. Okay.
This is a good theorem to try to prove on your own, a very good theorem.
Okay.
Okay, now we're ready for the last theorem. This is called the Bolzano-Weierstrass theorem.
I think we already got it down.
No.
Let
me see real quick. It should be. Where is it? No, it must be down here. There are some other theorems, like there's the Cauchy condensation. It's not that important. I'm not going to worry about that. But where's the Bolzano-Weierstrass? Here it is. Yeah. This is the last one. So the Bolzano-Weierstrass says something a little bit different. What it says is that if you have a bounded sequence, there has to be a convergent subsequence. This is a little bit different.
Yes.
Okay, so notice how many definitions there are, right?
Yes.
Okay, so this is the last theorem. This is like the monotone convergence theorem, but it's a little bit different. Notice what it says. It says that if it's a bounded sequence, it doesn't say that the sequence converges. It doesn't say that, but it says that there's a subsequence. So what is a subsequence? It's like
it says
yeah.
Every bounded sequence contains a convergent subsequence. Okay.
This is a sequence that's a subset of the original sequence.
Like what we have before, B subset of A.
Kind of like that. So let me show you how this works, okay? So let's go ahead and take a look at this sequence. We looked at this sequence a second ago. It was equals -1 to the nth, right?
Yeah.
So we know that at -1, that's equal to x sub 1, x sub 3, x sub 5, right?
Yeah, all the odd numbers.
Exactly. And +1 is equal to x sub 2, x sub 4, x sub 6, etc., right? This is a bounded sequence, right?
Yes.
Tell me the bounds. What are the bounds for this sequence?
The upper or the lower?
Well, bounded means that it has to have an upper and a lower.
-1 and 1.
Exactly. Right. These are right. So this is clearly a bounded sequence, right?
Yes.
Is there a convergent subsequence? Is there a part of this sequence that's also a sequence that converges?
So we need to show it's converge or not.
Right. I want to claim
so because it's bounded, it should converge.
Well, the sequence won't converge. We know for a fact this sequence does not converge. The sequence itself doesn't converge. But what I'm going to claim is that there's a sequence within this sequence that does converge.
Could you write that? Like, what?
So what this says is that there's a sequence within the sequence. This is what a subsequence is. That converges. There's
what this
there's yeah no I'm sorry. Go ahead.
What this mean? I mean, I didn't get it.
Okay, so I'm going to show you. Here's a convergent subsequence.
Okay.
Because these sequences converge. This sequence converge. This is a subsequence, right? It's actually a sequence. It goes on forever, right?
Yeah.
It's part of the original sequence, right? So this is a subsequence. And it clearly converges to -1 because everyone in there is -1, right?
Yes.
All right. And notice that the same is true for this guy. This is also a subsequence too, right?
Yes.
And it also converges to +1, right? Okay, so that's how it works.
Okay.
It says that if the sequence is bounded, there has to be some sequence in that sequence that actually converges.
It says that's bounded, but we don't care if it's converged or not. But yeah, there is a sequence, so like a subsequence.
Yep.
Okay.
Now, sometimes the sequence is the whole. Now, sometimes the subsequence is the whole sequence. I'll give you a really simple example. Suppose we look at this sequence here. X sub n is equal to 1 over n. Okay? Is this a monotonic sequence?
Monotonic mean decreasing or increase.
I'm sorry. Is this a bounded sequence? Sorry, is this a bounded sequence?
Yes.
Sure, it's bounded.
Yes, it is.
And we know, and so we know that there's a convergent subsequence by the Bolzano-Weierstrass, right? So this is clearly bounded. It's bounded between 1 and 0, right?
Yes.
And so we know that there's some subsequence that converges, but it turns out the subsequence is the whole sequence, right?
Yes.
Because this is x sub 1, x sub 2, and we showed that this guy actually converges to 0. Okay.
Yes.
So sometimes the subsequence is the whole sequence, but we have to prove that. We don't know that. All we know is that there's a subsequence. We don't know it's the whole sequence yet.
Yes. Okay. I do understand that.
Okay. So these are the main theorems. These are the main theorems that we really have to understand. Very important.
Okay. Cool.
So let's see. So do you have the exam that he gave you that you took?
Not now. Not with me now.
Okay.
But yeah, let me check. Maybe
because I was going to say if you had it, we could actually work those problems because he's very likely to give you something like that, you know.
Yeah, I have it.
Okay, great.
So,
do you want to take a snapshot and send it to me?
Yeah, I can take a picture and send it to you.
Okay.
Hey, you wanna buy the email?
Yeah, sure. And I can just open it up real quick and we can take a look at it.
Yeah, no problem.
Okay, great. When is your next exam? Do you know?
Maybe after 3 weeks.
Okay.
But I told you I'm stuck in 2 homeworks. So I need your help by those.
Yeah, that's really important. The sequences are really important. You really want to understand those. Now, those are the homeworks you're talking about, or they're homeworks after, right?
It's in chapter 2.
Okay.
And the other is in chapter 3.
Good.
But I need you. So I will send you 2 questions, and
sure.
we will do the other next time.
Sure. That sounds good. Yeah, this is the sort of thing you have to understand the basics really well, and once you understand it, you'll find it's not that difficult. Everything has to do with sequences. You can understand everything from sequences.
Yeah, you're right. But so could you like if I send the homework problems,
mm-hmm.
you pick 2, like there's 2 homeworks,
mm-hmm.
1 and 2.
Mm-hmm.
Okay, you pick 1 or 2 question from 1 and not solve it, but you doing a trying solve by sequence and those stuff like, and send it to me. And same thing for the homework too. I just want to like show him I'm trying to solve, not solve, but I'm trying.
I'm not quite sure I understand what you want.
So I will send you the homework.
Mm-hmm.
You choose 1 or 2 question or 3 question,
mm-hmm.
and you write you're trying to solve, not solving, but you're trying, like by use theorem 1.3 and like trying to solve but not solve.
Let me make a suggestion, because You know, one of the things I noticed in talking to you is that you catch on pretty quick. Once you have the idea, you understand it pretty well.
Yes.
Here's what I would suggest. You know, look at the problem and try to start it. You know, try to make a start. Show me what you have, and I'll give you a hint. I'll say, okay, try this. So I'll kind of give you an idea of what to do. And then you try it. And if you get stuck, we can kind of go through it. You know, because here's the thing. I want you to try to do as much as you can. And I just kind of like give you little hints.
Yeah, I do understand you. Yeah, that's what I'm thinking about.
Okay.
But I'm really behind. So I'm late to submit the 2 homeworks. I need to submit them, and then for the other homework I will do what you suggest.
Okay, that's an excellent idea. So you want me to take like 2 problems from each of them and basically kind of write out the solutions, right?
Yeah, but not really solve. Just show that you are trying and stuck or something.
Okay.
I'm sorry about that, but
that's okay.
Yeah, I'm late for that, so
that's no problem. Now, did you send the pictures? I'm not seeing them.
Yeah, I sent.
You sent it to MT Brennan? Oh, here it is. It took a long time. I don't know why. Okay, that's okay. All right, so let's see real quick. Oh, good. You did it as a PDF. Good.
Yes.
Makes it much easier. Okay. And you know what I can do if you want is I can make like a little video, kind of like what we're doing now, if it helps you to understand it.
For what we have done here in this meeting?
Right. For this one, but also for the homework.
Okay, if you can do that, that would be helpful.
Okay, so let's take a look at. I'm going to open a new page here. Let's start a new page.
Okay.
Okay, so these are the problems. Okay. Now here's one thing that's nice. So sometimes when you do these problems, you can do a counterexample, okay? This is a good problem. And he likes these a lot, I can tell you, because I've worked with a lot of people with ELO. He loves this sort of question. Prove or disprove, okay?
Yeah.
Now, so what he's asking you is this. He's saying that you have some sequence xn. It's a real sequence, right?
So he said let's xn donate to a sequence of reals. Okay.
And I know that the even part of the sequence converges. The terms in the sequence that have even indices, they converge, right?
So he said if the even converge and the odd converge, and as n goes to infinity, then xn converge as n goes to infinity. So he gives the even and the odd and ask about just n. Is that what he means?
Right.
Okay.
So if this is true, then is it true that the whole sequence has to converge? Okay.
Okay.
Now we actually just did a problem that answered this question.
Okay.
Right?
Mm-hmm.
Do you remember the problem we did?
Yeah, I think so.
Okay.
Not quite sure.
Which problem did we do that answers this question? We just had a... Yeah, no, I'm sorry. Go ahead.
I'm not quite sure what we should use here.
Okay, notice we just had a problem where the odd sequence converged, the odd subsequence, because this is a subsequence, right?
Yeah.
We just had a problem where the odd subsequences converged and the even subsequence converged, right?
Yes.
Okay, because that so what sequence was that?
subsequence or a sequence subsequence of a subsequence.
That's right.
Like, yeah.
And this is where x sub n was -1 to the nth, right?
Yes.
So this is a situation where x sub 2n converges to +1, right?
Yeah.
The odds
converge to -1.
But the sequence itself does not converge.
Yes. Yes.
So we have a name for this. We call this a counterexample. This is an example that shows this theorem is not true, right?
Yes.
Okay, good. So the answer is no, and we use a counterexample.
Okay.
See, notice that a theorem is a very, very delicate thing. A theorem always has to be true, right? So if this was actually true, we'd have to say every time we had a sequence where the odd subsequence converged and the even subsequence converged, it always has to be true that this converges, right?
Yes.
So to prove it wrong, you only have to find one example where that's not true, right?
Yes.
And that's how a counterexample will work. It's kind of like if your mother says to you, "You never clean your room," right?
Mm-hmm.
In order to prove her wrong, you only have to find one time.
Yeah.
Right? And then she's wrong. Okay. All right. So let's look at the other one here. Let's see. He likes those sorts of problems a lot. Where is it? Here it is. Okay. Prove or disprove. This is a good question. This is a hard question. Okay.
Okay, let's do it.
Okay. Some things in real analysis are kind of tricky because you have to know certain tricks. So here's a trick that you have to know.
Okay.
Let's look at what the theorem is saying first. So the theorem is saying that you have some sequence x sub n, right?
Uh-huh.
And you define some new sequence that's x sub n plus 1 minus x sub n, okay?
Okay.
So if we had x sub 1, x sub 2, x sub 3, x sub 4, ... right?
Okay.
This new sequence would be x2 minus x1, right?
I didn't understand.
Okay, so this is saying, whoa, hold on, I gotta put my battery in. Whoa, hold on. Didn't know it was so low. 1 second. So notice that we're making a new sequence from the old sequence, right?
So what's the old sequence? It says xn as a sequence of reals.
Mm-hmm. That's our old sequence.
So you take an x1, x2, x3, x4.
Mm-hmm.
Okay, the set yn equal xn plus 1 minus xn.
Mm-hmm. So what is y1? Y1 is equal to, when this is 1, this is 2, right?
Yeah.
Okay. And so then y2 will be x3 minus x2, right?
Yes. Yes. Okay. ...
Okay. So we're looking at the difference of the neighboring sequence elements, right?
Okay. So it says yn converges.
Right.
Then xn converges to
So what we want to prove or disprove. If this is true, is this true? Okay.
Okay.
Okay. So this is a little tricky. So here's the counterexample. The answer is no. Okay.
Okay.
This is a very special counterexample. If you didn't know this, if you didn't see this, you wouldn't know this. It's a tricky counterexample, but it's a very important one. Here's the counterexample. The counterexample is that x sub n is equal to the square root of n.
Okay.
Okay, so let's be careful. Let's look at this, okay? So y sub n is equal to xn plus 1 minus xn, right?
Yes.
So that's equal to the square root of n plus 1 minus the square root of n, right?
Yes.
Okay, what I'm going to do something a little tricky. I'm going to multiply the top and bottom of this by Okay. And when I do that, I'm going to get n plus 1 minus n. Okay, because this looks like a minus b times a plus b, right?
Yeah.
Which is a squared minus b squared. And then this looks like this. Okay? And so these n's cancel, and I get this.
Do you know how I cannot see?
Oh, sorry. Yep. Okay. So when I multiply, okay. So notice that this converges to 0. Yn converges to 0, right?
Yes.
Okay. And we can actually prove that using the Squeeze theorem. So you can show that Yn converges to 0. But notice xn does not converge to anything. Xn diverges.
Okay, how is that?
Because notice that xn is equal to the square root of n. This is unbounded, right?
Yes.
This goes to infinity. So xn is unbounded, therefore it cannot converge, right?
So how do you know it's unbounded?
Because the square root of n gets bigger and bigger and bigger. It doesn't, if you look at the function, the square root of n, right? It goes like this, right? 1 is 1, 4 is 2, okay?
Okay.
And it keeps getting bigger and bigger and bigger and bigger. And so this thing goes off to infinity. So any sequence that's unbounded can't converge. We said that earlier, right?
Yes.
So therefore, xn does not converge. Okay. So that's the counterexample. Yeah. I found a sequence where this converges, but this doesn't converge. So that's a counterexample, right?
Yeah.
So that proves that. Okay. So notice he likes those sorts of problems. And notice the answer is not always yes. Both of the answers were no there, okay?
Yeah.
So you have to really know what you're doing. But this is a really important this is an important problem. This comes up in analysis a lot. This is a really good problem to know. Okay.
Okay.
And I have to be honest with you. This is something that most people, when I took analysis, I couldn't prove this. I had to be shown this specific example. It's tricky.
Yes, it is.
Okay. He gave you that on an exam?
Yes.
Oh man.
Yeah. This is crazy.
That's a hard problem. Okay. All right. Okay. What do you say? Is that pretty good?
Yeah, that's pretty good. I should. You're gonna send me the papers and the video.
You bet.
So I can study tomorrow.
Yep. It takes a little while because the video is long. I'll put it on YouTube, but I'll set there's a thing where you can set the permission so only you can watch it.
Okay, just yeah. It talks like, could I have it tomorrow?
Oh no. I'll do it tonight. It takes about a half hour for it to.
Okay, I will study tomorrow. I will study and write what we have. Right, and understanding, and
Excellent.
So I keep touch with you. Good. And I will send the complex homework to you.
When do you get the complex? Do you get it on Thursday?
No, I think yesterday she did send it.
Okay, yeah, send that to me as soon as possible.
We have to submit it. A day after Monday. I don't know what's the name for that day.
Oh, you mean Tuesday, right?
Tuesday, yeah.
Yeah. Okay.
Okay.
Can you send that tonight?
Yeah, I will send it right now.
Excellent.
The homework for complex. I will send also. You have the book. This book?
Yeah.
Okay. I will send the problems to you. You pick the easier one and try to solve.
I think that's a really good idea.
Okay.
Sounds
just good. The easier, like 2 or 3 problems from each homework.
Yep.
So just try to solve it. And send me the try. I can write it, and yeah, if you can take a video of it, that would be great.
And the main thing is you don't want to remember all the theorems. If you know these 4 theorems, I'm going to try to do everything just using these 4 theorems. These are really powerful theorems, okay?
Okay. I will tomorrow study them very much.
Excellent.
So about, we have done 2 hours.
Sure.
So it's 40.
Yeah,
Yeah. So about the complex homework, I don't know what's long is it. I'll send it to you and then see and tell me, okay?
Sure.
So about the price, okay?
Sure. No problem.
Okay, thanks a lot.
Alrighty.
Today was so helpful. Yeah, we can meet tomorrow.
Yeah, I have someone from 7 to 9, but I'm free before that or after that. So you're free from 1 to 6?
Let me see my schedule here. Could I bring my schedule? Just give me 1 minute.
Sure. Take your time.
Thanks.
I'm going to stop the video. Yeah, I'll leave it running.
Okay, so you said free from where to where?
Let's see, from like 3:30 to 6, I'm free.
From 3:30 till 6. Let's do 3:30. Yeah, 3:30.
That'll work.
Okay. 3:30.
So you have prayers at 1, right?
Yes.
Okay. All right. Good. That'll work out.
Okay. And tomorrow we're gonna schedule another appointment till we cover chapter 1, chapter 2, 3, and the homeworks, and we keep doing the real.
Good. And here's the thing. And here's the thing you want to remember. Elo's being really nice. He's really trying to make sure you understand it, and you can definitely do it. But don't give up. He's really trying to help you.
Yes.
He's a good guy.
I'm bad in real. I'm good in the other subjects.
Okay.
Especially the applied math. I'm good at them. But real proof, we haven't studied proof really and back home. So that's the problem. We're stuck here.
It's very hard. It is.
Yeah. And also the language for us is really big problem.
Yeah.
I used to be a really, really good student.
You are?
I got a job before I graduate.
Wow.
Because I was really good. But in Arabic, but here I don't know. Also, I here easily give up because I just want to go home.
Here's the thing. Now you have an Arabic version of the real analysis book, right?
Yeah, we do have.
Okay, but here's the thing. The test is going to be in English, so it's okay to use that. But in the end, you have to be able to.
Yeah.
You can use it as like an aid, but you have to understand English in the end.
Yes.
I know it's hard.
Yeah.
I couldn't.
Here's
the thing. I couldn't do what you're doing. Okay, there's no way I could learn your language. It's very hard. It is, but you're doing good.
Hopefully, yeah. Thanks.
All right, inshallah.
Inshallah. Okay, so I will send the homeworks to you tonight. See you tomorrow.
Yep.
Okay.
And I'll send all that to you tonight, so you'll be all set.
That's cool.
Great.
That's Tell me about the price, please, huh?
Sure. No problem.
I just wanna not be late for like giving you money, so okay. I wanna give you. Well, like you're teaching me. I need to be also very, very nice, like because you are so nice to me, teaching me. I don't need to be late to giving you money.
I appreciate that. Thank you.
Okay. Thanks a lot.
Okay. All right. Have a good night.
Okay. Have a good night.
All right. See you tomorrow. Bye-bye.
See ya. Bye.